Welcome to Lesson 8E, How to Reduce Induced Drag and Why. In this lesson, we'll discuss some undesired consequences of tip vortices, and then we'll look at various ways that we can reduce induced drag and the strength of these tip vortices. First, I'll list some undesired consequences. The first one we've already been discussing all along is induced drag. In a previous lesson, I also mentioned cavitation in tip vortices in ship propellers. It turns out that these tip vortices are a problem for aircraft in the wake of another aircraft. Consider an airplane that's generating tip vortices because of its lift, and consider another airplane that's located somewhere near this tip vortex. The high speeds from the vortex can greatly affect this smaller airplane. It can flip it over or cause structural damage that can lead to a crash. There have been a few commercial jet accidents attributed to wake vortices. Here's a couple of them. Flight 427 in 1994, where a 737 was landing too close to the wake of a 727, and 132 people were killed. Here's a newspaper clipping. The journalist says wake vortices, which he calls horizontal tornado-like air currents swirling off the aircraft's wingtips. I guess that's a reasonable description of a tip vortex. They were investigating whether that was a factor in the crash of this airplane. More recently, in 2001 in Miami, an Airbus A300 was behind a Boeing 747. 260 people were killed in that crash, again due to the tip vortices. So, because of all these consequences of tip vortices, how do we reduce the induced drag and the tip vortices? First, I'll comment that you cannot eliminate induced drag entirely. Why? Well, as we discussed previously, for a 3D lifting body, like an airplane, we have lift, which means there's a bound vortex on the wing and a starting vortex at the airport, and also trailing vortices, or tip vortices. These are unavoidable, but we can reduce induced drag for a given required lift. How? I'll list several methods. Number one, make the wingspan very long. I'll illustrate with a diagram where wingspan S is much bigger than the chord C. Throughout most of this wing, the bound vortex strength gamma A is nearly constant, since it's nearly 2D over most of the span. Of course, this bound vortex turns and produces the tip vortices at the wing tips, as we've been discussing. The total lift L on this wing for an almost 2D body is rho U gamma A times S. In other words, it's proportional to S. And induced drag dI is proportional to the wasted kinetic energy due to the high speed in these tip vortices, as we also previously discussed. Notice here that lift goes up linearly with wingspan S, but induced drag is independent of S. Instead, dI depends on aerodynamic circulation gamma A. Therefore, for a given lift requirement, which depends on the weight of the aircraft, gamma A goes down as S goes up. We can see this clearly in this equation, since L, rho, and U are constant. Increasing S and keeping everything else fixed requires a smaller gamma A, and induced drag goes down as gamma A goes down. So we conclude a longer wing has less induced drag for a given lift. I'll show you many examples. We see very long span wings on human-powered or pedal-powered aircraft, solar-powered aircraft, high-altitude long-endurance aircraft, sailplanes, and even migrating birds. Here are some examples of human-powered aircraft. Notice how long the wings are compared to their chord. Here are some examples of solar-powered aircraft. This, by the way, is called a flying wing. Here are some other pictures of various solar-powered aircraft designs. This zigzag one is kind of cool looking. Here's another one with a very long wingspan. Here are some other examples, namely sailplanes. Human-powered planes produce a very small amount of thrust. Solar-powered planes produce a little more. Sailplanes don't have any thrust at all. So some of them have incredibly long wingspans compared to their chord length. Here's a bird example. The Arctic tern flies all the way from the Arctic to the Antarctic and back, pretty much the whole way around the globe every year. Notice how long its wings are compared to its body. Another way to reduce induced drag is to vary the wing geometry. The basic principle is to make the circulation gamma A come off the wing in a distributed manner, in other words, not concentrated at the wing tips, as is the case for a sharply cut off blunt wingtip. How do we do this? One way is to vary the chord length C with span. This is called taper. Instead of a straight, constant chord wing, we have a wing with a larger chord at the root than at the tip. We can also vary the camber with span. For example, you might have a high cambered wing at the root here, where camber means the curvature of the wing, but a smaller cambered wing at the tips. A highly cambered wing has more lift, therefore more lift near the root. A differential lift near the root is larger than one near the tip. Of course, you'd have to integrate dl over the entire wing to get the lift. Another option is to add twist. Again, comparing the root and the tip. The root has a higher angle of attack than does the tip, again leading to more lift near the root compared to the tip. In most actual aircraft, all three of these occur simultaneously. The wing is tapered, cambered differently from root to tip, and twisted, and all three lead to more lift near the root compared to the tip. In all these cases, the overall gamma A around the entire wing must be the same gamma A in the tip vortices, but the tip vortices themselves are more spread out or not as concentrated, so this distributed vortex would have less wasted kinetic energy than would a non-distributed tip vortex. And as we've talked about previously, less wasted kinetic energy means lower induced drag. I'll ask the students what are some other benefits of these geometry modifications.
Is it because tapered, twisted wings look so much cooler, dude?
Perhaps, Joe, but that's not why they do it.
I think there would be less weight on the tips.
Right, Arnold. Less moment or torque yields a structural advantage. From a structural standpoint, we eliminate the huge moment due to lift near the wingtips. There's also a stability advantage. Twist and camber modifications, for example, will make the airplane stall at the root first. The ailerons near the wingtips can remain operational. Ailerons are important for roll control, by the way. If stall occurred near the tips first, we would lose this control. A third way to reduce induced drag is to add winglets at the wingtips. These are kind of like little wings that bend almost vertically at the tips of the wing. This has a similar effect as the other mechanisms we talked about. Namely, although we still have the same gamma A, the vorticity is more distributed or spread out, therefore less wasted kinetic energy, therefore lower induced drag. Again, I'll show some examples. We learned this from birds, where they often flare their wing feathers at the tips to reduce induced drag. You can think of this as a kind of winglet. In the case of a sailplane, you often see winglets, again, to maximize lift compared to drag, since there's no engine producing thrust. We also see this on commercial aircraft. The goal there is efficiency, to save fuel. By the way, here's the aileron that I mentioned. Next time you fly, you can watch this thing go up and down as the airplane rolls. Here's some more examples of sailplanes with winglets. A student sent me this one, which is kind of large, and my colleague Mark Mommer here at Penn State is a world expert on winglet designs for sailplanes. Finally, NASA did some experiments many years ago with tip turbines. The idea was to make these turbine blades turn and generate power, taking advantage of the tip vortices. This results in lower induced drag, again by disrupting or diffusing the tip vortex, while also producing some power. Sounds like a cool idea, but the weight and complexity of the tip turbines cause this technique to be not so practical. So we don't see these on any modern commercial aircraft. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.